Hi everyone, and welcome to another video of this channel. So today we will investigate a very simple triangle geometry problem, which is more like a teaser. It's not like a problem like I've been doing in other videos. So, but it will have a very satisfying solution. So let's get started. We have this triangle ABC, and this angle A right here, its measure is 36, and then the measure of angle B is equal to the measure of angle C, which is equal to 72 degrees. So this triangle right here is isosceles. And then we want to find what is AB over BC. Okay, so we want to find the ratio of this side to this side. And so basically, without loss of generality, we assumed first that BC is equal to 1, right? Because if we scale down this triangle, so like let's suppose that BC is some sort of value A, if we scale down the entire triangle so that BC will be equal to 1, that scales down this side by the same amount, and the ratio is preserved. So we can just assume that BC is equal to 1. So next, AB is equal to X, right? So we're finding X right now, right? AB over 1. So then we draw this bisector of angle B right here, which intersects AC at D. And then just by basic angle chasing, right, it's given that C is 72 degrees, and then D is also 72 degrees. And then A is 36 degrees, that's given. So then note that BDC is isosceles, so BD is also equal to 1, and so is AD, because ABD is also isosceles. But now notice that ABC and BCD are similar. So this big triangle right here is similar to this smaller triangle right here. And from this, we can infer, right, that the ratios of their corresponding sides are equal. So AB over BC equals BC over CD, which implies that CD is 1 over X. So CD is 1 over X. But then notice, right, X is equal to AB, but then since ABC is isosceles, AB is equal to AC, which is equal to AD plus DC, which is 1 plus 1 over X. So it turns out that X is equal to 1 plus 1 over X. So X squared minus X minus 1 equals 0, and X is equal to 1 plus or minus the square root of 5 all over 2. And of course, 1 minus the square root of 5 over 2 is negative, but X is a ratio we want to be positive, so we forget about the minus root. And this is equal to phi. Phi is the golden ratio. So 1 plus the square root of 5 all over 2. Now, why is this such an important number? So this answer right here is the golden ratio. So now, why is this number so important? Well, I'm just going to do a quick demonstration of the golden ratio right here. So this right here I have illustrated is a problem that people as far back as the ancient Greeks contemplated. So let's suppose that there is this segment of length A that's divided into two parts, one of length 1 and one of length A minus 1. And then the Greeks, they wanted to find, okay, so what is A such that the ratio of A to 1 is the same as the ratio of 1 to A minus 1. In other words, the ratio of the entire segment to the big part is equal to the ratio of the big part to the little segment. And basically just by multiplying both sides by A minus 1 and then subtracting the 1 over, we get that this yields A squared minus A minus 1 equals 0, and A is equal to phi. That's the golden ratio. And so just going back to our discussion about the ancient Greeks believed that this was probably the most aesthetically pleasing ratio. In fact, looking at many ancient Greek buildings, such as the Parthenon, one can see that its longer side of its facade is 5 times more than the shorter side. So, and this phi is a Greek lowercase letter. But then this number phi isn't like a mathematically arbitrarily chosen constant. It appears in nature a lot too. So first I have to explain what the spiral thing means right here. And the spiral is called the Fibonacci spiral. So the Fibonacci sequence, basically we represent it with f. So the kth term of the Fibonacci sequence is fk. So the 0th term of the sequence is 0, and then the first term is 1. And then the second term is the sum of the first two terms. So f of 1 plus f of 0 is 1. In a similar manner, we get that f of 3 is f of 2 plus f of 1, which is equal to 2. And then f4 is f3 plus f2. which is equal to 3. And then so on. We can just do this forever. F5 is equal to F4 plus F3, which is equal to 5. Then F6 is 8. F7 is 13, and so on and so forth. And basically, we can just say that f of k plus 1 is equal to f of k plus f of k minus 1. But the place where where this golden ratio shows up in this sequence, is the fact that as k gets extremely large, like it blows up to 1 billion or something, the ratio between f of k plus 1 and f of k gets closer and closer to 5 right here. And so this number right here, it's a really crucial constant in the Fibonacci sequence, which in turn has a lot to do in nature. For instance, this spiral right here, it gets larger and larger by a factor of 5. Right, and this spiral appears in nature a lot too. See, there's the Milky Way, then plants, seashells, even hurricanes. But then, maybe like a purely mathematical application of phi is its continued fraction. So basically, what is 1 plus 1 over 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 1, and so on and so forth on to infinity? Well, this thing does in fact have a value, and it is in fact true that since this is an infinite continued fraction, its value is irrational. Let's suppose that this is equal to x, right? Well, notice that this circle thing I have in orange is also equal to x. So then we have that 1 plus 1 over x is equal to x, and this is exactly the condition for the golden ratio. We have that x is equal to phi right here. And basically, so this number is really omnipresent everywhere in math and in nature, probably maybe even to the scale of pi or e. And so probably what amazes me the most is that it shows up even here, which is why actually a lot of sine and cosine values for multiples of 36 have phi in them. So I hope you like this video. Thanks for watching, and I'll see you next time.